So hello friends. So today I am going to give a proof of a corollary of the last theorem which we discussed. Okay, so in the last class we discussed the theorem. So before going to our corollary, I am going to actually sum up the previous concepts which are actually needed in our discussion, today's discussion. Okay, so first you have to remember what is homotopic part. So homotopic part, actually I am going to give some example. So direct homotopic part. So these are gamma naught and gamma 1. These are two closed rectifiable part. Close, the beginning and ending points are same. Rectifiable, that is this can be measurable, that is it has finite length, something like that. So gamma naught and gamma 1 are homotopic. This is the symbol for homotopic. Gamma 1 is homotopic to gamma 1 or gamma 1 is homotopic to gamma naught, same thing, because we already established that this homotopic relation is an equivalence relation. So gamma naught is homotopic to gamma 1 means gamma 1 is homotopic to gamma naught by symmetricity. So here gamma naught and gamma 1 are homotopic because you can continuously deform gamma naught and you will get the curve gamma 1. Similarly, if I continuously deform the curve gamma 1, then you will get the graph gamma naught. Therefore, this is the concept of homotopy. Okay, this is the concept of homotopy. So this is the concept of homotopy in terms of closed curve, actually. Okay, in terms of closed curve. So we already in the last class we discussed the concept of actually simply connected region. So simply connected region, this is the definition of simply connected region. An open set G is simply connected if G is connected and every closed curve in G is homotopic to 0. Okay, every closed curve in G is homotopic to 0. So roughly speaking, in terms of example, so in the pictorial representation, this is a simply connected region. This is a simply connected region. So if I consider any closed curve, this is actually homotopic to 0. Okay, so homotopic to 0 means it is homotopic to a constant curve. Okay, if I consider any closed curve, it is homotopic to 0, that is it is homotopic to a constant curve, something like that. So here I have given, this is a multiply connected region, so we are not interested in this part, we are interested in simply connected region. Simply connected region, this is the simply connected region. So if every closed curve is homotopic to 0, then that is every closed curve is homotopic to a constant curve, then the region is said to be simply connected. Of course, it must be connected as well as open. Okay, connected as well as open. So here you see the concept of this homotopic to a constant curve. So here gamma naught is a constant curve, that is the straight line. This straight line is a constant curve, because you can see within this domain set, gamma naught of t, that is gamma naught of t is always this distance. So okay, so this is constant, always constant. So again, if I consider this circle, then this circle is homotopic, that is gamma is homotopic. Or you consider this closed curve, this gamma is homotopic to gamma naught, because you can continuously deform this. Okay, continuously deform this and you will get this straight line. So gamma is homotopic to gamma naught, and which is a constant graph. Okay, so therefore the gamma is homotopic to 0. Gamma is homotopic to 0. That is the concept of homotopic to 0. So simply connected region means it must be open set and it is connected and every closed curve is homotopic to 0. So last class we define this. Okay, then we have this immediate statement of Cauchy-Fork theorem. So what is the Cauchy-Fork theorem? If G is simply connected, then integration along gamma of f equal to 0 for every closed rectifiable curve and every analytic function f. Okay, so here gamma is a closed rectifiable curve, closed that is beginning and ending points are same, rectifiable, that is it is a finite graph, that is we can have the length of the curve, and every analytic function of f, for every analytic function, so every analytic function we have this integral equal to 0 for a simply connected region. So this is the fourth version of Cauchy's theorem, which we use to establish this corollary actually. Okay, if Z is simply connected, already we established this result in the last class. If Z is simply connected and F is a mapping from Z to C, which is analytic in Z, then F has a primitive. Okay, then this F has a primitive. Okay, F has a primitive, say F has a primitive capital F. F has a primitive capital F means what does it imply? F has a primitive capital F means F dash equal to F. Okay, capital F is a primitive of F. So this is the definition of primitive. This is integral. Okay, F is said to be integral of F, something like the primitive. So we have this theorem from the last class. Z is simply connected and F from Z to C is analytic in Z. Analytic is in Z, then F has a primitive in G. So using the Cauchy's theorem, fourth version, we establish this result. Okay, now we are going to take help of our next result. So what is the next result? Next corollary, actually this is the next corollary. Okay, the statement of the corollary is Z is simply connected. First condition, Z is simply connected, and let this is an analytic function, F is an analytic function such that Fz is not equal to 0 for any Z in G. Okay, so for any Z, okay, for any Z in G. So, okay, so therefore Fz is not equal to, this is a non-zero function for any Z in G. For every value, F of Z is equal to non-zero. Then there is an analytic function G. There must always exist an analytic function G. That is the conclusion from Z to C, capital Z to C, such that F of Z can be written as exponential of this analytic function Gz. Okay, F of Z can be written as. So this we have to establish. Okay, if you can establish, then this is the another consequence of this establishment. So what is the next consequence? If Z0 belongs to Z and exponential of Z0 is equal to Fz0, then we may choose Z such that Gz0 is equal to W0. That is, if we choose Gz0 is equal to W0, we have to show that EW0, that is exponential of W0, is equal to F of Z0. Okay, we have to establish this part from this establishment. Okay, so given condition Z is simply connected, F is an analytic function such that Fz is not equal to 0 for any Z in G. Then there is an analytic function Z. We have to find out an analytic function Z satisfying this condition. So what is this analytic function Z? So using this, we are going to establish the next actually consequence. So from the given condition in the proof, you can see from the given condition, Fz is not equal to 0 for every Z. Fz is not equal to 0 for every Z. So we can think about Fz F dash by F, because quotient structure, you can think about a quotient structure F dash by F, because Fz is not equal to 0, that is denominator is not equal to 0. Okay, so therefore what is F dash? What is F dash by F? So F dash by F is F dash by F function is nothing but, if I take the image, then this will be F dash Z divided by F dash Z divided by Fz. Since Fz is not equal to 0, so you can think about this concept. Okay, F dash of F. This is true for any Z. Therefore, since Fz is not equal to 0, denominator is not equal to 0, therefore this function is analytic, because F dash is analytic. It is given that F is analytic means F dash is analytic. So you just remember what is analytic function. F is analytic means F dash is continuous. That is derivative, already derivative exists and F dash is continuous. And we know that if F dash is continuous, then all derivative exists. That is, F is analytic function means all derivative exists. So F dash is analytic, automatically F dash analytic. So F dash analytic, F is analytic. So quotient of this analytic function is again analytic. Okay, so by the previous theorem, the previous theorem, that is previous corollary, that is if Z is a simply connected f is analytic function, then f is a primitive. So here f dash by f, here f dash by f has a primitive by the previous theorem. So the z1, say this is the primitive z1 because this is an analytic function. Okay, and it is defined in the analytic function is defined in the simply connected region. So it is a primitive, say z1, that is z1 dash is equal to f dash by f. Okay, so now you consider the exponential of z1 of z. Okay, so exponential of z1 is equal to, say, hz. This is the exponential of exponential function of z1 of z. Now z1 is analytic, exponential function is analytic, so composition of two analytic function is again analytic. Therefore each function is also analytic. Okay, so h is an analytic function, and also h never vanishes, that is h is not equal to 0 for any value of z. Hz is not equal to 0 because this is an exponential function. Hz is exponential function never equal to 0. Okay, so complex exponential function never equal to 0, so h never vanishes. So again you can think about this concept f by h, because h never vanishes for every z. So f quotient h, so this is again analytic function. Okay, analytic composition of this quotient of the analytic function is analytic. So now you consider derivative of this analytic function. So you just remember the quotient of derivative. So this is sz, this is the formula, hz square hz f dash z minus f dash hz h dash z fz. Okay, so what is our h dash? H dash equal to h dash is nothing but this is our h is this is our h. Okay, h is this, so h dash is automatically h dash is nothing but exponential of z1z into z1 dash z. So this part is nothing but h, this part is so z1 dash. So we have f h f dash minus f h dash. So if I put the value of f dash, what is our f dash? So f dash from here you can have the value of f dash. So f dash is nothing but f z1 dash, and h dash is nothing but h z1 dash. So these two terms are cancelled, so this part is 0, that is automatically this is 0. So you can have this derivative of f of z is equal to 0 for every z. Derivative of f quotient h of z is equal to 0 for every z. So therefore this function must be a constant function. Okay, for every z this function is a constant function. So f is equal to ch, this is the constant, f is equal to ch. And for any function, okay, any function h, we have a result is c is not equal to 0, then c can be written as exponential of c dash. Okay, we have a result, so this result, so c can be written as exponential of c dash. Since hz is not equal to 0, okay, if hz is equal to 0, then automatically fz is equal to 0. Okay, but fz is not equal to 0 by the given condition. So hz is not equal to 0. Since hz is not equal to 0, therefore you can write down hz in terms of some exponential function, exponential of z1 of z. Okay, hz is not equal to 0, exponential of z1 of z. Okay, so hz, sorry, hz already we have hz is equal to exponential of z1z. Hz is nothing but exponential of z1z. But for this constant c, because c is a complex number, therefore c can be written as exponential of c dash. We have this result. So in place of c you can write down exponential of c dash. So exponential of this can be written as exponential of z1 dash plus c dash for some constant c dash. Okay, for some constant c dash. So if I consider let zz is equal to z1z plus c dash twice by ik, okay, then you can see exponential of zz, this is equal to exponential of z1z, this, just put the value. So by exponential property, this is exponential of a plus b, same with exponential of a into exponential of b. So this is exponential of z1z plus c dash and exponential of twice by ik. So but this is equal to 1 because exponential of twice by ik means what? Exponential of twice by ik. So exponential of twice pi ik, exponential of twice pi ik, this is equal to cos of twice pi k plus I sin of twice pi k. Okay, I sin of twice pi k, but this value equal to 0, twice pi k, so this is 0. Now this value equal to 1, even multiple, and this value equal to 0. Okay, so this is equal to actually 1, this value equal to 1, this value 1, so therefore this is nothing but fz. So our actually so we get this function gz, which is the function gz such that exponential of gz equal to fz. So we have the first part, and second part, if we are going to assume that gz naught is equal to w naught, we have to establish that e to the power, that is exponential of w naught, is equal to f of z naught. So I have assumed that z naught is equal to w naught, therefore then e to the power w naught, then e to the power w naught is equal to e to the power gz naught, but e to the power gz naught, this is equal to exponential of gz naught by this exponential of gz naught is equal to f of z naught, hence the result. Okay, this is the recorded result. Thank you.